Hi, my dears. Good morning. Welcome to today's talk about X-ray diffraction. X-ray diffraction. It simply read as X or D. X-ray diffraction is a laboratory-based technique commonly used for identification of crystalline materials and their characteristics. It is a laboratory based technique for the identification of crystalline materials and their study of other characteristics like unit cell, their parameters of ABC, atomic packing factor, and their dimensions. These type of characteristics will be analyzed by this XRD technique. It is a laboratory based technique. Why X-rays used for this diffraction? X-rays were discovered by Röntgen, who call them X-rays because it is unknown experiment. Uh, is not invented this X-rays wantonly. While he's doing the experiment, he found some unknown rays in his experiment. So he called that unknown rays or X-rays. They are also called as Röntgen rays. The first diffraction, X-ray diffraction, was discovered by Max Onley in 1912. The first X-ray diffraction discovered by Max Onley in which year? In 1912. X-rays are electromagnetic radiation. They are electromagnetic radiation with wavelength in the range of 0.1 to 100 angstrom. 0.1 to 100 angstrom. The wavelength of X-rays is between 0.1 to 100 angstrom. X-rays are used to produce the diffraction pattern because their wavelength is typically the same order of magnitude as the spacing between the planes in crystal. In crystal, whatever spacing is there to the spacing, this X-ray wavelength is matching. That is the reason we are preferring X-rays for the diffraction in crystal analysis. X-ray diffraction is widely used in geology, environment science, material science, and engineering. Where it is broadly used, apart from physics and chemistry, it is used in geology, environment science, material science, and engineering for the purpose of identification of unknown crystalline substances and their characteristics. What is the application? What are the applications of XOD? To identify crystalline phases and orientation, to determine structural properties like lattice parameter, strain, grain size, epitaxy, phase composition, preferred orientation, thickness of thin films, and the multi-layers thickness, determination of atomic arrangement. So for these are applications of X or the X-ray diffraction application, lattice parameters, phase and orientation, strain, grain size, epitaxy, phase composition, preferred orientation, thin film thickness, and multi-layer thickness, as well as atomic arrangement. See, in this concept, one of the important thing is that Brock's law and its derivation. Brock's law states that the X-rays reflected from different parallel planes of crystal interfere constructually when the path difference is integral multiple of the wavelength of X-rays. That means when you take a crystal, the crystal planes the crystals are arranged in parallel planes. The planes of crystal are arranged in parallel. So these parallel planes distance or spacing we define as d, and this spacing simply represented with the path difference, that is we can consider as 2d sine theta. So path difference is equal to integral multiple of the wavelength. That means 2d sine theta equal to n lambda. So n lambda equal to 2d sine theta, where n is the integral. That means n equal 1 to 3 integer, lambda is the wavelength, d is the spacing between two planes which are in parallel setup. Angle is incidenting angle. Theta is the angle between two planes along with the incident ray. Where n is the integer, lambda is the wavelength of X-ray, d is the spacing between the planes, and theta is the angle between the incident ray and scattering plane. And now derivation of Bragg's law. Consider a crystal made up of equidistant parallel planes of atom with interplanar spacing d. So the crystal is made up with the parallel planes of atoms with their planar spacing is how much? Interplanar spacing is d. Let a wavefront, let a ray of monochromatic electromagnetic ray or X-ray beam of wave length fall at an angle on these atomic planes. So what is the spacing between d, that is atomic planes? So if the ray is incident on these atomic planes, then each atom scatters the X-rays in all directions. Then what is happening when the ray is incident on this between these two planes which are in parallel setup? When the rays are enter, the rays will be scattered by the which rays? X-rays are scattered by the atom of crystal in what direction? In all direction. In certain direction, these scattered radiation are in phase. So the whatever X-rays are scattered or diffracted, few are in phase. So when they are in phase, phase means in orderly, in orderly, fewer in phase. Whenever they are in phase, they will be constructively interfere, and the rest of the one are destructively interfere. Fewer in phase, the phase one are constructive interference, and fewer in out of phase, they is considered as the destructive interfere. So here the rays are incidenting. So we have the ABC triangle, along with the we have another construction, that is BZ. Then there are two triangles are formed, ABZ as well as BZC. So the incident angle is what? Theta, and reflecting angle is what? Theta. Between two planes, whatever distance is there, that is d. So here ray 1, ray 2. Between ray 1, ray 2, what is the angle is there? Theta angle is there. So that is we simply define as d sine theta. So the path difference between ray 1, ray 2 is equal to what? Between two rays, the path difference can be assumed to be 2d sine theta. The rays of the incident beam are always in phase and parallel up to the point at which the top beam strikes the top layer at the bottom Z. So here we are going to, so this figure about the derivation point of view. Now how you got n lambda equal to the sine theta. For that we need to construct a construction. Here from B to Z we drawn a line. So here it shows that one, the incident, the AB is incident, BC is the reflected one. Here, when incident is over, then reflected from the B. The second beam continues to the next layer. The second beam continues to the next layer where it is scattered by the atom. So first beam enter from A to B. Again from B to C it is reflected. So see, this is the construction part. So A, B, C. See, from this one A, B, C you take AB enter and BC is reflector. So AB is enter into the medium that is striking at the B. From the B along the BC ray, it is emerging out the ray. So here from that figure we can analyze. So AB Z, from the ABG triangle, the beam is travel from A to B, B to C. So it is considered ABBC. So A plus B, the ABBC is equal to the summation of A and B path is equal to integral multiple of the wavelength. That means integral multiple means integer of multiple, that is integer of lambda. So that is n lambda. So that's why AB plus BC is considered n lambda. N lambda equal to what? AB plus BC. But we know that from the figure ABZ triangle, we concluded that D is the hypotenuse of the right angle triangle ABZ. From the trigonometric concept, D is related to the angle to the distance AB and BC. The distance AB is opposite to the angle B. So you can consider from the trigonometric concept, you consider AB equal to what? AB equal to D sine theta. But from the same triangle, AB is equal to whom? AB is equal to PC because the incident ray is equal to reflected ray according to Snell law. So AB equal to BC. So therefore n lambda equal to AB plus BC, that is AB plus AB, that is 2AB. Therefore the above equation changes to n lambda equal to 2AB. But AB equal to what? From the previous concept, AB equal to d sine theta. Then n lambda equal to d sine theta plus d sine theta, which is equal to 2d sine theta. N lambda equal to what? D sine theta plus d sine theta, which is equal to 2d sine theta. N lambda equal to 2d sine theta. Over. So now experimental method for the diffraction methods. So what are the diffraction methods? So right now you talked about the Brock statement. Now we are going to talk about diffraction methods. So what are the diffraction methods? So there are three diffraction methods. We have Lay method, rotating crystal method, powder method. Lay, rotating, powder method. Let's see what is Lay method. Lay method is, in this method a single crystal is held. A single crystal is held stationary in the path of radiation of continuous wavelength. In the path of radiation of continuous wavelength. While theta kept constant, the angle is kept constant. The wavelength is what? Lambda, but it is varied. The lambda is varied. Then a plain film receives the diffracted beams. A developed film after is exposed shows in the diffraction pattern. A lay method is constructed. The method is only used for the single crystal, where the crystal is fixed upon the single crystal. The X-rays are incident. When the X-rays are incident on the single crystal, few of the X-rays are transmitted and few of the X-rays are reflected. So after that, when they are incident on the crystal structure, crystal body, on the single crystal, and reflection as well as reflection as well as transmission. So from that particular, few of the X-rays are reflected, few are the transmitted. Then after from the crystal, the refracted rays are exposed or fell down on a particular screen where you are placing the screen. So the rays are exposed on a screen. So when you develop the screen, you will be find a certain pattern. That certain pattern is called lay method. So here the X-rays are incident on a crystal. The crystal is what? Fixed crystal, and it is fixed. That is the reason the theta is constant. It's not, there is no movement in the crystal. It is in fixed condition. It is a stationary crystal. Upon the stationary crystal, the rays are exposed, and when the rays are exposed, which rays? The X-rays are exposed. When the X-rays are exposed, few of the rays are transmitted, few of the rays are reflected. After reflector and transmission, the rays are which are passing through the remaining rays which are passing through the crystal are exposed on a photographic film. When you develop the photographic film, you will be find a certain pattern. That certain pattern is called as lay pattern. You can see the center one is very bright because of the constructive interference. When you go away from the center, you will be see non-brightness. That non-brightness is indicating distractive interference. So here the lay method is how many types? The lay method is divided into two types. One is the transmission method. The other one is the back reflection method. So here what is transmission method? A beam of X-ray is passed through the crystal. After passing through the crystal, X-rays are diffracted and scatter recorded on the photographic plate. Here, few of the X-rays are transmitted through the X-ray, transmitted through the crystal, the single crystal. So whatever X-rays are transmitted to the single crystal are exposed on a photographic film. So this is photographic film, and the rays are exposed through the crystal to the photographic film. Here we have one more example where the X-rays are incident in the prism. Then from the prism, the rays are diffracted, and after that you can see a particular pattern on the photographic film. When you develop, you will be find this type of the photographic film. So each dot on the photographic plate represent the position of atoms. So this is about the LAM method in transmission. So briefly about this one, the brief thing is that in this transmission lay method, the film is placed behind the crystal to record the beams which are transmitted through the crystal. One side of the cone of lay reflection is defined by the transmitted beam. The film is intersect the cone with the diffraction spots generally lying on the ellipse, so ellipsoid form, and can be used to orient crystals for the solid state experiment. Most suitable for the investigation of preferred orientation sheet, particularly by the confined to the lower diffraction angle. To the lower diffraction angle purpose, we are using this one. So coming to the next one about the back refraction method. This method provides similar information as the transmission method. You can see that when the rays are exposed on a crystal, but the rays are bounced back to the same direction. This is called the reflection method. Briefly, you can see from this figure. In the back reflection method, the film is placed between the X-ray source and the crystal. The beam which are diffracted in the backward direction are recorded. One side of the cone lead reflections is defined by the transmitted beam. The film is intersect the cone with the diffraction spot generally lying on the hyperbola, that is on ellipse. This is an hyperbola. This method is similar to the transmission method. However, back reflection is the only method for the study of large and thick specimen. It is for the large and thick specimen. It is not valid for the big crystals. And second experiment is rotating crystal method. What is rotating crystal? See, the X-rays are there. The X-rays are incident on a crystal. The crystal is a rotating form. When the crystal is rotating form, you will so few of the rays are diffracted, and those who are passing from the crystal will be exposed to the particular screen. When you develop the particular screen or photographic film, you will be find a certain pattern. That pattern is indicating a rotating crystal method. In this method, a single crystal is rotated about the fixed axis in a beam of monochromatic. The angle is here it is rotating. In the previous one, the angle is it is in a constant. Here it is rotating. That is the reason the angle still it is in continuous status. The angle is a variable. The angle is variable. So while variable, but the thing is that in the previous condition the lambda is vary, but here lambda is constant. In the previous condition, the theta is constant, but here the theta is changing. So the variation of angle theta due to the rotation of crystal begins different atomic planes in the crystal into position. Different atomic planes in the crystal in the position. The variation of angle theta due to the rotation of crystal brings different atomic planes in crystal into position. To record such reflections, a film is mounted on a cylindrical holder that is concentric with a rotating spindle. So, spindle. To record such reflection, a film is mounted on a cylindrical holder that is concentric with a rotating spindle. So, this is about the which method? This is here the you need to understand two things. Here theta is variable and lambda is constant. Fodder method. This method is useful for the samples that are difficult to obtain in single crystal method. Those the crystals which are in solid state. So to that materials purpose means they are first they are converted into fine powder method, and the fine powder is cal- calculated or collected to the a particular transparent glass. Thereafter, these rays are exposed. Then the ray exposed diffracted. The rays are diffracted by this crystalline powder atoms, and the diffract rays will be calculated or counted by the debye camera. So from that condition, we are using X-ray detector. From the X-ray detector, we need to calculate that the values of the powder method angles. Sorry, the values we are going to calculate. So in powder X-ray diffraction method, into the method first, the method was introduced by German scientist. His name is Tibe, sorry, both the German scientists are introduced. That is German scientist Tibe and Schiller introduced this method. So the powder diffraction is a scientific technique using X-ray diffraction on powder sample for the structural characterization of material. For the purpose of what? To diffract the powder materials. Powder diffraction is used. It is a scientific technique. So this powder measurement instrument is called powder diffractometer. So powder diffractometer, what is the powder measurement instrument is called as a power diffractometer. Let's see what do you mean by diffractometer. A diffractometer is a measuring instrument for analyzing the structure of material for the scattering pattern produced when a beam of radiation or particles interact with it. So here it is completely analyzing for the crystalline materials, those who are in powder nature. So diffractometer is what? Diffractometer is nothing but it is an analyzing instrument for the what? For the diffraction. What is diffraction? Like scattering pattern. Here we have the diagram. The X-rays there. The X-rays are passing through the slit S1, S2, and incident on the crystal, which is in the powder status, incident on the specimen, where P is considered specimen. After that, you will be see the rays are diffracted. The exposure rays are calculated by a photography film. Then, when you develop this photography film, you will be find certain arcs. A diffractometer produces rays at known frequency of X-ray source. When these rays reach the sample, the incoming beam is reflected and transmitted through the crystal surface, further diffracted by the atoms present in the sample. Here, diffractometer produced rays at a known frequency. What is known frequency here? The X-rays or the known frequency source. So these rays are incident on the sample of powder nature, which the sample is what? Powder sample. When the rays are incident on this powder sample, few are transmitted, few are reflected. Thereafter, further, the rays will be diffracted because of the atoms present in sample. If the atoms are arranged symmetrically with the separation distance d, these rays will interfere constructively. If the separation between two planes or the atoms is d, then they undergoes constructive interference. Therefore, that means path difference is 2d path difference 2d sin theta is equal to integral or integer multiple of the wavelength. Integer or integral multiple of the wavelength. That means n lambda equal to 2d sin theta and producing a diffraction maximum according to Braggs. So maximum diffraction means bright spot indicating maximum diffraction as per the Braggs and lambda equal to 2d sin theta. If the rays interfere directly at point between the intersections, there this is an out of phase segment. If they are in out of phase, this is because of the in phase you will see bright spot. Because of out phase you will be see non bright spot. So this is about the two-dimensional pattern of the powder refraction, where this cone is considered as a Debye cone, and this the image is plane detector 1. The angle between the beam axis and ring is called scattering angle. The angle between beam axis, X-ray beam axis, and scattering ring is called beam axis, and cone ring is called scattering angle. Here it is we taken as 2 theta. Why we taken in X-ray crystallography? It is denoted as 2 theta. In X-ray crystallography, it is denoted as 2 theta. According to the Bragg's law, each ring is correspond to particular reciprocal lattice. According to whom? According to the Bragg's law, each ring corresponds to a particular reciprocal lattice vector A, reciprocal lattice vector A in the sample crystal. According to Bragg's law, the above conversation can be considered as A equal to Q to K sine theta, which equal to 4 pi by lambda of sine theta, where A is a reciprocal lattice vector, Q is the length of the reciprocal lattice vector, K is the momentum transfer vector, theta is the alpha of the scattering angle, lambda is the wavelength of the source. Wavelength of the source. So it is briefly explained. A source is A is the source of X-rays. The X-rays are generated by cathode ray tube. The X-rays are generated by cathode ray tube. X-rays are filtered by monochromator. So here monochromator, mono means what? Single. So they are filtered by monochromator to produce monochromatic radiation, and means the remaining rays colors will be absorbed, and it's passing only one color. That is the reason it is called monochromator. And monochromatic ray is passing through the monochromatic radiation is passing through slit S1 S2. It helps to choose correct wavelength. Means a suitable wavelength will be uh, set by the monochromator. So here the radiation is passing through the slit S1 and S2 are used to adjust the shape of the beam. What shape must be there? The shape must be narrow condition. So must be in the narrow shape. Collimate, collimate to concentrate the direct the X-rays X-rays beam toward the sample so that the powder specimen get narrow pencil of X-rays. Pine powder is stuck on a hair by means of gum. So the powder, whatever you collected, that you stick with the gum. It is suspended vertically in the axis of cylindric camera. This enables the sharp lines to be obtained on the photography film, which is surrounding the powder crystal in the form of circular arc. The X-rays, after falling on the powder, passes out of the camera through the cut in the film so that minimize the fogging produced by the scattering of the direct beam. When the geometry of the incident X-rays impinging the sample satisfy the Bragg's equation, construct interference occur, and the intensity of the reflected X-rays is recorded by the recorder. That is nothing but detector we are placing behind that experiment. So that will be collecting, the detector will be detecting the diffracted rays. The detector also passes this X-ray signal and convert into the count rate, which is then output to the a device such as printer or computer. Most of the things are connected to the computer device nowadays. So in computer device, the output of computer will indicate how many rays are diffracted, that everything will be counted. So if the angle of incidence is theta, then the angle of reflection will be 2 theta. It is the incident theta, then it will be 2 theta. Here we are taking that one 2 theta. Already in the previous slide we discussed it. In X-ray crystallography we are going to consider 2 theta. So if the radius is the r, circumference is 2 pi r corresponding to the scattering angle from the above figure, it can be considered theta equal to 2 pi r into 1 by pi r. From the above equation, the values of theta can, so from all the previous conditions, we are going to evaluate the theta value. Then it will be substituted in the Braggs equation and calculating the value of d. So finally, a sample of hundreds of powder crystals show that diffracted beams from continuous course. So They are all the diffraction rays in the powder diffraction method forms cones. A circular film is used to record the diffraction pattern. So here we are going to use circular film in the diffraction pattern. Each cone is intersect the film giving diffraction lines. So whenever it is intersecting, it is giving diffraction lines. These lines are in, so you can see arcs in the film. So this is about the beam entry, beam existing. This is the pattern of this powder method. The bright one because of the constructive, and later one the brightness is going to be decreasing. So that is because of the destructive. Thank you.